All right, let's dive into one of the most important and, beautifully wrong ideas in the entire history of science. We're talking about Niels Bohr's model of the atom. It was this revolutionary idea that solved a puzzle that was just stumping everybody. And it all kicked off with one simple but kind of terrifying question.
So, picture this. It's the early 1900s, and we've got this new picture of the atom. There's a tiny little nucleus in the middle, and electrons are orbiting it, almost like a miniature solar system. It's a great image, right? But there was a massive problem. According to all the known laws of physics at the time, this picture was completely, totally impossible.
Okay, so here's the fatal flaw. In classical physics, an electron whipping around in a circle is always changing direction. That means it's accelerating. And an accelerating charge is supposed to radiate energy. It should literally glow. But if it's losing energy, its orbit is going to shrink. It would start this death spiral, crashing into the nucleus in like a trillionth of a second. If that were true, nothing should exist. You, me, this screen, it would all just collapse.
So, yeah, physicists were staring down the barrel of an impossible atom. They had a model that seemed right, but it predicted that all matter should just, poof, disappear. Clearly, something was fundamentally wrong with the old rules.
And this is where our hero, Niels Bohr, a Danish physicist, just explodes onto the scene in 1913. He didn't just try to patch up the old model. Nope, he basically proposed a whole new set of rules for how the world works on an atomic scale.
What's so amazing is just how bold this was. You have to appreciate the guts it took. Bohr basically looked at the most trusted laws of physics, the rules of electromagnetism, and said, you know what if, down here at this tiny scale, they're just wrong? He just decided to ignore the prediction that the electron should be radiating away energy.
So he built his new model by grabbing some of the most cutting-edge and, let's be honest, seriously weird ideas floating around at the time. He took Max Planck's idea that energy comes in these little packets, or quanta. He grabbed Einstein's discovery that light is made of particles called photons. And from this, he made his big move. He said that electrons can only exist in special, stable orbits where, for some reason, they just don't radiate energy. He called them stationary states.
And this whole idea completely changed our understanding of how atoms and light interact. It wasn't about these slow, graceful spirals anymore. No, it was all about sudden, dramatic jumps.
So the key concept here is quantization. I want you to imagine the energy levels inside an atom aren't like a smooth ramp. They're like a staircase. An electron can be on step 1, or it can be on step 2, or step 3, but it can never, ever, ever hover in the space between the steps. Each step is a very specific, allowed amount of energy. That's it.
Now, everything in the universe likes to be at its lowest, most stable energy state. It's just lazy, I guess. For an atom, that means the electron wants to be on the lowest possible step of that staircase. We call that the ground state. It's the atom's default setting, where it's happiest and most stable.
Okay, so this leads us to the famous quantum jump. Here's how it works. If a photon of light comes along with the exact amount of energy needed to get from, say, step 1 to step 3, the electron will absorb it. And bam! Instantly, it leaps up to that higher energy level, what we call an excited state. But it's not stable up there. It almost immediately wants to fall back down. And when it does, it spits back out that extra energy as a brand new photon of light. And the color of that light perfectly matches the size of the drop it just took. I mean, this was a truly bizarre, totally counterintuitive theory. It was breaking all the rules of classical physics. So the big question was, how on earth could Bohr prove any of this?
Seriously, think about it for a second. He's proposing these invisible energy staircases and electrons that basically teleport between them without ever existing in the space in between. To the physicists of his day, this must have sounded like absolute fantasy. He needed some hard, cold, undeniable proof.
And he found it. He found it in the light from a hydrogen atom. See, for decades, scientists had known that if you heat up hydrogen gas, it doesn't just glow with a continuous rainbow. Instead, you see these very specific, sharp lines of color. It's like an atomic fingerprint, and nobody could figure out why. Well, this is where Bohr's genius just hits you. He sat down and did the math for his model. He calculated the energy of the light that would be emitted when an electron jumped between his imaginary steps. And the result? His calculations predicted a pattern of lines that was a perfect line-for-line match with the real-world fingerprint of hydrogen.
And he hadn't just gotten close. He had, starting from his wild theoretical ideas, mathematically derived an equation that was identical to something called the Rydberg formula. Now, this was an equation that other scientists had cooked up just by looking at the data. It worked, but nobody knew why it worked. Bohr had just provided the why.
The reaction was, as you can imagine, immediate. This couldn't be a coincidence. The level of agreement was just astonishing. All of a sudden, this crazy, weird model with its quantum jumps had to be taken seriously. Why? Because it worked. It just flat out worked. And to really put a fine point on it, Bohr's theory let him calculate the value of something called the Rydberg constant. This was one of the most precisely measured numbers in all of physics back then. And Bohr's number, calculated from his theory, matched the experimental value with incredible accuracy. This was the smoking gun. There was no denying it now.
But, and there's always a but in science, as incredible as this was, the story doesn't end there. Bohr's model was a crucial stepping stone, but it wasn't the final answer. It was, as we said, a beautiful but flawed idea. So let's be super clear about what it got right. For hydrogen, with its simple one proton, one electron setup, the model was a total home run. It also worked perfectly for things like a helium ion that had lost one of its 2 electrons. Basically anything with just 1 electron orbiting a nucleus.
The problem was, the moment you tried to use it on the next atom up, helium, which has 2 electrons, the model just broke down, completely. It just had no way to account for the complicated pushing and pulling between multiple electrons.
And even its most basic picture, the idea of electrons zipping around in neat, tidy, predictable orbits, that turned out to be wrong too. The full theory of quantum mechanics, which came later, showed us that electrons actually exist in these fuzzy clouds of probability, not on fixed little racetracks.
So if it was wrong, why do we still talk about it? Why do we celebrate it? Because even though the model itself got replaced, its core ideas became the absolute bedrock of our modern understanding. The idea that electron energies are quantized, that the staircase exists, the idea that an electron's energy goes up the farther it is from the nucleus, and most importantly, that those mysterious spectral lines are a direct result of these quantized energy levels. These are the cornerstones of all of quantum mechanics.
And for giving us these absolutely essential insights, for completely changing how we see the atom, Niels Bohr was awarded the Nobel Prize in Physics in 1922. His beautiful mistake had shoved physics onto a brand new and much more interesting path.
And that really leaves us with a final thought, doesn't it? The Bohr model was, technically speaking, incorrect in its details. And yet, it was absolutely essential to get us to the right answer. It just goes to show you that sometimes scientific progress isn't about being perfectly right from the get-go. Sometimes it's about being brilliantly and productively wrong.